Welcome to the third lecture in my Mechanics of Materials course. In this lesson, we will be looking at mechanical stress, which is a crucial concept that is studied in Mechanics of Materials. So, what is stress? Well, you might be familiar with emotional stress that humans feel during intense situations. And so, you can think of that same analogy for mechanical stress, because stress in mechanics is defined as the intensity of an internal force that acts on a plane or area passing through an arbitrary point. So again, it's the intensity of an internal force acting on a plane through a point. So to sort of visualize stress in general, let's say we have a metal cylindrical rod, like so. And now this circular section on top is the surface of this rod, and a compressive force is applied onto this surface, just like so. And now we can of course consider this surface or plane as an area. And now if we were to conceptually cut this rod, say about somewhere here, we would be able to analyze the stress that is generated internally by this force. And now the average stress from a force is generally defined as simply force per unit area, which is just mathematically force F divided by area A. So that is practically the average stress throughout this rod. So again, remember force per unit area. And also remember that this area is the cross-sectional area of the material of interest. And now a more specific type of stress is one known as normal stress, which is represented by lowercase sigma. Normal stress is, again, an intensity of a force, but specifically one that acts normal to a surface or plane, which we can again consider as an area. So, let's say we have this surface or plane with an area, and there is a force that acts vertically upwards, perpendicular to the surface, in the normal direction to the plane, which we could consider as acting along the longitudinal axis, just like so. And now let's say that this is the same direction as the y direction. In this case, we can say that the force is normal to the area or surface. Again, simply because the force acts in the same direction as the normal direction to the surface. So in that case, we can predict that we will have a normal stress, sigma. And now normal stress, sigma, contains two indices in notation. And this first index represents the normal direction to the plane. And now this second index, which I'll go ahead and write in a different color here, it represents the direction of the internal force. So in that case, the first index will be y, because the direction of the normal to the plane is in the y direction. And now the second index will also be y, because the force, of course, also acts in the y direction. So that leaves us with sigma yy equals, of course, we said stress is force per unit area. So we'll have force F, more specifically Fy, over the cross-sectional area A. So that defines the average normal stress for this example. Now, just for some practice here, let's try a different example, except this time this is the x-axis. So we'll have force Fx, and in that case, our normal stress will now be sigma xx equals Fx over A. And now just a couple of things to keep in mind. Whenever a normal force tends to pull on an area, kind of like how we see in this example, this means that the stress will be tensile, since of course the force pulls away from the area, which basically means the force is in tension. So this will look something like this. So that is a tensile force with a tensile stress. And now, in contrast, whenever a normal force pushes on an area A, then we will of course have a compressive stress, which of course, if you recall, this is the opposite of tension, since this is a force that pushes down on or compresses an area, just like so. So again, a pulling force correlates to a tensile stress, and a pushing force correlates to a compressive stress. Now, another type of stress is shear stress, represented by Greek letter tau. And again, since this is a stress, it is the intensity of a force, but this time one that acts tangentially to an area A. So again, previously, normal stress was of a force that acts normal to the area, and this time it's tangent to the area. And so let's go over a visual example so that we can see what a tangent or shear force would look like. So again, let's say we have a surface with an area just like so. Based on your knowledge of trigonometric terms, what do you think a force tangent to this area would look like? Well, something tangent basically means that something barely touches a surface at a point, such as a line to a curve. And so in this case, this is a force that sort of slides over this area, just like so, barely touching the surface. And so this force essentially acts along this surface parallel to the tangent plane. And this is a force known as a shear force, hence shear stress. And now, of course, this force is now perpendicular to the normal to the plane. And let's just go ahead and label this as the y direction again. And let's say that the force acts along the x direction. And so therefore, tau will have the indices y, the direction of the normal, and x, the direction of the force. So shear stress tau yx is equal to F over area A. Oh, and more specifically, this force is Fx. And now keep in mind that this is fundamentally the average shear stress. Just like how previously sigma yy equals Fy over A is the average normal stress. Whereas if we wanted a more accurate definition for individual shear stress, it will be tau yx equals the limit as a change in area delta A approaches 0 of delta Fx over delta A, which of course is for every infinitesimal change in area. But generally, we will focus more on average shear stress. And likewise, a more accurate normal stress would be sigma yy equals the limit of delta A approaches 0 of delta Fy over delta A. And now let's quickly go over the units of stress. The SI units for stress are typically newtons per square meter. And of course, this is because stress, again, is force per unit area. So the standard unit of force is, of course, newtons, and area is square meters. And also for SI units, keep in mind that 1 Pascal is equivalent to 1 Newton per square meter. And so you might be familiar with pascals being a unit of pressure, and so that sort of hints that stress and pressure are pretty much related and basically interchangeable. And now we also want to take note of a few basic metric prefixes that we will commonly encounter throughout this course. Starting off with kilo, K, which is equivalent to 10 to the power of 3. And next we have mega, capital M, which is 10 to the power of 6. And lastly, we have giga, capital G, which is 10 to the power of 9. And so, for example, if we have 1 megapascal, that'll simply be equal to 1 times 10 to the power of 6 pascals. So these are prefixes that are important to memorize. That way you can swiftly go through problems throughout this course. And now for English units or US customary units, if we wanted to translate force per unit area using English units, we would end up with pounds per square inch, which is of course where the unit PSI comes from, which you might be familiar with here in the United States. So the standard English unit of pressure or stress is PSI, which again is just the abbreviation of pounds per square inch. And now similarly, using prefix kilo, we have the unit KSI, which is basically kilopounds per square inch. And so of course, remember that kilo is 10 to the power of 3, so 1 kilopound, or kip, is equivalent to 1,000 pounds.